So our goal is eventually, I shouldn't say eventually, one of the things that this course is often used as I've said this before, I think the first week I made a big point about this. You know, much of what most humans think mathematics is really not what math is. You guys, most of your lives are sitting in a math class doing lots of procedural things over and over and over again. Lots of, sort of techniques and cookbooking. And in the big scheme of things, that's really not mathematics. That's a piece of math. But really, mathematics is more or less, I shouldn't say more or less, that's a bad way, but one of the more important pieces of mathematics is having a rigorous structure and being able to use what we call proofs to verify things. So yes, we want to be able to do computations, but we also want to know that these computations are logically sound, and we want to know why they're logically sound. And so what this class, whether it's here at La Roche or many other schools, one of the goals of a class like this, as I've said, is twofold. One, to introduce you to a few different branches of mathematics. And as we're introducing you to a few different types of branches of mathematics, we're also introducing you to sort of the heart and soul of mathematics, and that is the proof, the idea of proofs. And so, that's sort of where we're at. So why am I saying that right now? Well, this leads us to back to homework set 3, which, after the first 2 assignments, why did they change the color? This is interesting. Did I do this? Anyhow, I'm looking at Canvas. It's no longer red, it's blue. It's like we went from the Bloods and now we're the Crips to steal another shenanigans. Okay, now for some reason this computer takes forever to download. I don't quite understand why it's not automatic. Okay, so anyhow, this homework 3 is basically here's the kind of things that we're going to be doing the rest of the semester. Doing things what we call proofs. And one of the ideas that I'm really trying to impress upon you is when we think of mathematical statements and we say things like, prove that this is this, or if this, then that, what we're constantly trying to get you to do is appreciate the logic that's sitting behind it, the P's and the Q's that we talked about, and the conjunctions and the disjunctions in those truth tables. Anyhow, with that being said, let's get into it. So we left off with this famous problem that it's worth us doing together, and that is proving that the square root of 2 is irrational. So this is sort of like the famous first proof that we often encounter in a class like this. It's, as I said last week, this statement in proof dates back thousands of years. Lots of different cultures understood it. Usually it's credited to Euclid, I think, because that was like the first book that it ever showed up in. Of course, maybe if you learned this somewhere else, they say, no, in our book in Japanese or in Russian or something, we figured it out before you Westerners quit stealing or that kind of stuff. I don't know. Typically it's taught, or at least in my, where I gotten my information from, I believe the first place this shows up is Euclid. But in Euclid, when we say Euclid, that's sort of like the quintessential first science book, Euclid's Elements. It was, it was basically about geometry, but if you imagine all those years ago, we didn't have science the way we do now. I mean, it was really like, what did humans see? They saw the stars and they understood shapes and stuff. And so that's what they talked about. There wasn't like heart surgeons, back then. There wasn't all these different ideas on germs and viruses and chemistry and all that. People were curious about certain things. But back then we were still trying to understand things like, stars and patterns of why does the sun come up and when does it go down, and how much land do we own, and what is the size of this shape, that kind of stuff. All right, nonetheless, we're getting off topic. So let's get right back into it, and let's do it. So here is the famous problem. So prove that the square root of 2 is an irrational number. So before we do this, we need to make sure we understand what this means. Most students, at least those who attended school in the United States, I have no idea what those of you who went to schools and other parts of the world, but part of like the mathematical curriculum, and I don't know if it's middle school or high school, it's probably talked about whenever you learn the connection between decimals and fractions. At least that's how it was taught when I was in school. You know, one of the things we try to teach students is if I give you a rational number, or as you guys think about a fraction, how do I write it as a decimal? And for example, we know that 1/2 is 0.5. At least we're told that. We know that 3/4 is 0.75. And then you learn this idea of how do I write a fraction as a decimal. One of the ways they would teach it years ago, especially before calculators, like when I was in school, and even now they should still teach it, is you do this sort of long division. You take the denominator, you divide it into the numerator, and one of the things you recognize what happens is either it terminates like with 0.5 or 0.75, or there is a pattern. For example, if you take the number 1 and divide it by, if you take the number 1 and divide it by 3, you end up getting a pattern. You get 0.33333, and that thing never ends. So let me explain this, because this is something I think a lot of us fail to appreciate. So the question is, what is an irrational number? So I asked you to do this for the homework, and probably what you did is you Googled it, or you looked it up in your book, which is what any good person should do if they're trying to learn. And then you likely copied it out of the book or off the Google machine. But you probably didn't think about it. So what I'd like us to do before we even think about answering this question, proving something, let's ponder what exactly is an irrational number. So we need to set this up properly. There's a correct way of setting the stage. And so what we'll do on the next page is the following. So let's define different types of numbers. So we've already talked about this before. So the integers are denoted. Remember, we use this bold-face Z. And the reason we use Z is because the German word for integer starts with a Z. I don't know what the German word is for integer, but let's Google it and verify for yourself. And if I'm lying, then tell me I'm lying. Perhaps I am. So what are the integers, though? These are the numbers 0, plus and minus 1, plus and minus 2, plus or minus 3, etc. So, and by the way, you've seen this before, but it's going to be sort of more important now. As you may know, it is convention to list them in brackets. So what do I mean by that? Well, it's convenient to list the integers like this. So we use this set notation, and we might we want everybody to know what this pattern is. So we might say like, we know that there's, at least intuitively, there's some sort of order to these numbers. So we might write it like this. So for those of you who've seen some sort of this kind of stuff before, maybe you have, typically anytime we have a collection of objects, in this case, it's a collection of numbers, we call that a set. It's a set of something. Just like at home, you might have a set of toys, or, the mathematical word for collection of objects is called a set. And the way we usually let the reader know we have a set is we put it in brackets like this. So we're going to assume that you guys are familiar with numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, forever. Those are called the natural numbers, the counting numbers. And then from these counting numbers, they each have a partner in crime that we call its inverse, particularly its additive inverse. So the number 1 has a partner named -1, and the number 2 has a partner -2. And that is its unique partner that if you add them together, you get 0. So we're going to assume that you guys understand these basic properties. And so if we take, now this is going to be scary, if we take all ratios of integers, we get the rational numbers. Now, the problem with the rational numbers is it's not so obvious how to list them in some sort of obvious order. So what do I mean by the rational numbers? We'll take any two integers. You pick an integer, I pick an integer. If we create a ratio or a fraction of them, if you will, we get what's called a rational number, 1 divided by 2, or 1/2. 3 over -4, or -0.75. So how do we do this, though? How do we define this? So the rationals are denoted by Q, and it's a bold-faced Q, and since it's hard to do that on a whiteboard, what we do is we sort of put this vertical bar here. And what they equal is they equal the following. They equal, now we can't list them. So the way we do this is we use what's called set builder notation. So I'm going to write something down. Some of you have probably seen this in a previous math course, depending on what kind of instructors you have. They may have used this notation. So what I'm going to do is I'm going to take the letter P and then I'm going to put it over the letter Q. So for those of you who haven't seen this before, let me explain how this reads. So this reads right here, the set of all numbers P over Q, where P and Q are integers. So one way to kind of make sense of this is anytime you see these brackets, think of it as saying this set of. Those brackets tell the reader that you're going to be paying attention to this collection of objects. In particular, we're thinking of any number that is a fraction. So you guys think of the word fraction because that's the word you learn when you're a student, but there's no correct. The official word for numbers that can be written as a fraction are called rational numbers. So typically what is taught in like what we call middle school or secondary school is that rational numbers are any decimal that terminates or has a pattern, and irrational ones are guys that don't. That's the way it was taught when I was in school. I don't know, maybe they taught you something very similar. For example, the number pi, 3.14159, goes forever and ever and ever. That is an irrational number. Now, I can tell you that. But if I said to you, prove to me pi is irrational, how could you show that? It's not very easy, actually. A lot of smart people spend a lot of time and long amounts of time in history before we figured that out. So those are the rationals. Does anybody have a question about this?
I guess my only real question is, I feel like I have no way of knowing how, other than the set builder notation, I have no way of testing any given number to know that it's an integer.
We mean to test that if it's an integer?
Right. How would I prove that any given number is an integer so that I know that?
Well, what do you mean? An integer, it's not difficult to prove something's an integer, right? What do you mean prove it's an integer? So the question was, how do I prove something's an integer?
Well, we had a statement that about how do we know if something is an even integer, and we had a statement.
Well, we have that definition. So, okay, so I think you're going back. At some point, you have to have a definition of something, right? So what we're doing is we're saying, okay, there's we're using, and I guess you could, depending on how you want to think about it, we're going to say there's these axioms. We're all going to agree that there are numbers out there. Let's start with how do we want to build them. Now, if you want to study the philosophical ideas of building numbers and what's 2 and 3, I mean, that's a whole nother world. You want to go take philosophy classes and do all that, that's fine. But let's just imagine our intuition. Let's imagine we're 5-year-olds. My 5-year-old knows that she has 4 Barbie dolls, right? She knows how to count 1, 2, 3, 4. She gets that. So it's an intuitive to her that integers exist. Well, excuse me, maybe not integers. Let's assume that the counting numbers are obvious to us. Right? In fact, they're so obvious, some people, you're going to be like, what the hell is he talking about? Of course, they're numbers, but it's not clear. I mean, think about how long it took humans to come up with a number system. Like, I don't know that you appreciate this, but the number system we use, using 10 digits, 0 through 9, that is not, we haven't had this since the beginning of humans. It's only about 800 years old that we've had that. Now, depending on what you believe, humans have been on this planet a hell of a lot longer than 800 years. So it literally took humans that long to figure up a useful number system, 10 symbols, which now we use 0 through 9, but it took us that long to figure out a useful number system. Now, before that, we just had different symbols. The Romans had the Roman numerals. Every culture had different, all kinds of cultures had number systems. But we figured out around 800 years ago or so is that the number system that we now call the decimal system was very useful because it was easy for humans to do what we would consider at that time efficient arithmetic. And then once we had this number system, we could invent things like algebra. We didn't have that before. It was really hard to do algebra and calculus. In fact, it would have been impossible to do any of that without a useful number system. So what we have to do is appreciate that our number system is not that easy to develop, but yet you don't appreciate that because your whole life you've known what numbers are. Like, let me give you an example of this. My kid, if I put 4, I've used this analogy many times. If I put 4 Barbie dolls on the floor and then I say, Lydia, go grab those other 2 on the other side of the room and tell me how many Barbies you have, she'll know that she has 6 Barbies. But if I write the symbol that us humans know, if I go to her, Lydia, what does this mean? The only way she knows what this means is if she's memorized it. That's it. She doesn't know. Now she knows that's the number 4, and she now knows that that's a plus sign, and she can read in her head 4 and 2 make 6. She knows that. But she doesn't make the connection with these abstract symbols in the Barbie dolls until she's had enough practice with it. See, that's what we fail to forget. Some of this stuff is intuitive. 4 plus 2 in symbols, that is abstraction. Humans created this. You know, how would Lydia do arithmetic now in her head? How does she know? She'll say 1, 2, 3, 4, 1, 2 Barbie dolls. Then she'll count them all up. She'll know 6 Barbie dolls. I mean, this is like these tally marks. This is how humans counted forever. And then we invented more efficient symbols. But this is not at all a new thing. Numbers, you know, and I think you're sort of hitting on it, Jared, is the philosophical idea here. At some point, we have to decide, what do we assume is we're going to be the rules because of intuition? Like, we're going to agree that the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 forever and ever exist. We agree. That's intuitive to us. Now we have to take a leap of abstraction because there's no concrete example of -5. Now you might say, I owe you $5, or there's something I can associate negative numbers with. But the point we all agree that we're going to add the negative integers into the picture, we are taking a leap of faith in the sense of we're going abstract. Okay, now that's great. Now we're saying pick any one of those numbers and then pick another one. And anytime you make a fraction out of them, that's called a rational number. So when you say to me, which was your original question, how do I prove something's an integer? We're not proving anything's an integer right now. We are saying these are the integers. The integers are 1, -1, 2, -2, 3, -3, 0, etc. Now, once we say this is an integer, we're making that definition. Then we define 2 types of integers. We define there's an even integer, and now there's an odd integer. I mean, think of the logical progression here. Now we're saying we're going to we're going to create a new type of number, a different type of number called the rational numbers. And what is a rational number? That is the integers, and if you want to say it in the 5th grade way, all the fractions. So the rational numbers are now all the integers with fractions. Now you're going to say, how is that an integer, p over q? Well, guess what? Take the number 7, divide it by 1, you get 7. 7 over 1 is the same thing as 7. It is a rational number. 14 over 2 is the same thing as 7. It is a rational number. Does that make sense? And by the way, why, you might say, why do we use q for rationals? Well, because that's in homage to the Italians. And the Italian word, it has something to do with like a quotient. Is the Italian word for quotient, obviously, we even in English, q, quotient, but the Italian, I think it's quotiente or something like that. Look it up. It ain't hard. Why do we use q for rationals? Let's Google it. Sometimes we have to just remind you guys that I'm not completely lying to you. Why do we use q for rationals? And here we go. Look, Cura has it. We'll trust these fools. I know this is Brainly. What this is. Yeah, there it is. Look, quotiente, Italian. Pino was an Italian. There you go. Pino was a great mathematician. See, this is what we learn. Let's see what this would be. Ah, look, even 2 people are lying to you now. Z for integers, because the German word Zahlen is number. Zahlen. Is that how you say it? Zahlen. Yeah, see, good. Speaking they Deutsch. All right. Okay. Very good. So, and by the way, not to get too far off the off topic, humans were cool with rationals way back in Euclid's days. We understood, they didn't write them the same way we did, but they understood that, yeah, guess what? You know, I use this all the time too. This is one of my favorite little demonstrations. If I have a stick, I can think of my stick as 3 equal pieces, making it 1/3, 1/3, 1/3. Here is 2/3 of my original thing. Right? So, you know, again, you might think it's silly that we're talking like this, but it turns out that this is quite important. And often I don't think that we appreciate Although maybe it will help you appreciate if you go back to when you were a kid, thinking about how difficult it was for you to learn certain things. Because a lot of this stuff is not intuitive. You know, and that's why there's a lot of people that argue what's important as a young person is to memorize things like multiplication tables and memorize simple arithmetic facts. That way you don't have to think about them, because once you start thinking, they get a lot more difficult. Okay. So here's where the fun comes in. If a number is not rational, we call it, creatively enough, irrational. Now, a very common thing is for you to say, well, give me an example of an irrational number. And of course, what any educated person will do is they know anything about this. They'll say, well, square root of 2 is irrational. They'll say pi is irrational. Remember that the fun number e that you maybe have seen in a calculus course, the e 2.7, that is a rational, or excuse me, irrational number. But to most humans, and this is how it was even back then, it was not at all clear that irrational numbers existed. So the famous story goes that, you know, you take Pythagoras' theorem. Everybody remembers that from high school. You have a side of a triangle, another side of a triangle, then you have a hypotenuse. Well, take a triangle where two sides are 1, and then if you determine the length of a hypotenuse, you get square root of 2. And this baffled those ancient cultures because the square root of 2, I mean, this is a philosophical nightmare too. You can't find a square root of 2 on a ruler. It doesn't exist. You can approximate it to any degree of accuracy, but the square root of 2 cannot be written down. You can't construct it with a ruler. And of course, you're going to say, well, what do you mean? I just took a square of side 1 and side 1 and cut it with diagonal. We're telling you, though, this is why it's the philosophical quintessential mind, you know what? I mean, books have been written about these classic Greek problems. And the story goes that Pythagoras, whenever someone, you know, one of his students or just sort of exhibited this proof that we're going to do shortly, they took him out to sea and killed him because they couldn't believe it. I don't know how true it is, but you can Google it. That's the story. So when you struggle with these ideas, when you keep thinking long and hard about what is he talking about P over Q, and what does he mean if you're if not rational, you're irrational, you should rest assured that it's okay that you have a lot of sort of difficulty grasping this, because it took civilization a hell of a long time to get there. So then what we say is all the rationals and all the irrationals form what we call the real numbers. So now this is sort of, we're not doing this in depth. So if we take all the rationals and the reals, or excuse me, and the irrationals, we get the reals. Or let me be more sort of. So the real numbers, again, you can't really write down in set notation what a real number is. The best you can do is sort of try to visualize it. And what we've done to visualize the real numbers is we think of a number line. So it's best to think about this, or it's useful. Oh. I hate when this thing goes rogue. So what do we mean by number line? Well, we take typical that we take a horizontal line, and then somewhere on the line we denote it to be 0, and then we say, okay, here's 1 unit, 2, 3, and then of course we might have -1, and you might have like -0.5. And over here you might say, okay, we know that this famous number pi is in here somewhere. You think about the real numbers as a continuum. It is a line that never begins, it never ends, and there's no holes in it. And that's another philosophical mind. You know what? And in fact, if you really, if to make yourself really feel better, the human understanding of the real numbers, sort of the number line, you can argue that it really wasn't sort of made rigorous until about 120 years ago. If you want to construct them, right? Construct the real numbers. I can sit here and tell you that there are no holes in this number line. And right now, this is probably lost on most of you. You're like, what is he talking about? We did the number line in 3rd grade, and it makes sense to me. But how do you prove the existence of a number that's not a rational number? And here's the wildest thing. I could ask you to give me 5 examples of an irrational number. You might be able to do that. But you could give me 1,000,000 examples of a rational number. But guess what? There's actually more irrationals than there are rationals. And you don't have to, you know, just take the interval from 0 to 1 and think about it. You know, break it into sort of pieces. How many pieces? And it's really, really, you know, you start taking advanced math, you learn some really cool things that often mess with your intuition. So anyhow, we don't want to get too far in advance, but the way I'll sort of put this bow on this right now before we do the problem is, there is nothing in your intuition, at least, that makes you think that there is at least one irrational. There's probably no intuition that you say, oh yeah, I can see there being a number that can't be written as a fraction. Now, hindsight's 20/20. You might sit back now and say, well, I heard about pi in school and I know pi is irrational. But if I said to you, why is it irrational? Could you do that? Could you tell me? And it wasn't obvious to most cultures on this planet that these things existed. All right, does anybody have a question? And I don't know, did I even answer your question originally? I mean, because maybe I'm misunderstanding you, but I'm not even quite sure what you mean by when you say, how do I prove something's an integer?
Well enough. I mean, I just was kind of thinking through, like, if irrational or if rational numbers are defined as an integer divided by an integer, can I use the definition of, I can't think, an integer now, can I use the definition of an integer as maybe a direction for a proof?
Well, right. I mean, so maybe, so the question is, how do I use the definition of an integer, I think is what you're saying, or how do I show something satisfies that?
Sure.
That's a great question. And the way I would encourage you to think about it, because look, you know, you've heard of the word axiom before, right? And so if you really want to nitpick, we have to decide, what are we assuming to be something versus what are we defining something to be? So I guess what I'm asking you to do at this point is just trust your intuition that there are integers. They exist. And how do we know you're an integer? Well, we know you are because you are. If I give you a number and it has no decimal expansion, it is an integer. You know, pick a number, pick any number you want. If I say 7/4, you say not an integer, right? If I say 16, you say integer. Why is it an integer? Because it's in your list of integers. 16.0 is an integer, right? So now but you have to be careful how you're saying it. I mean, 16.000000007 is not an integer. But if I say 16.0, well, why would that not be an integer? I mean, that's where we talk about things like place value, and maybe you might remember these things from a science class or high school, significant digits and all that stuff. Why does that matter? But right now, all I'm saying is let's all agree that there are these things called the rationals. Excuse me, the integers. And then if I just take any two of them and I form a quotient, I divide one by the other, we call that a rational number. So you could think of it as a hierarchy. There's the counting numbers, and then they fit inside the integers. And then the integers fit inside the rationals. And then if you take the rationals and all the guys who aren't rationals, which we haven't even showed one of them exists yet. We haven't showed there's an existence. That's the first. I mean, that's really what we're doing when we show the square root of 2 is irrational. We're showing there's at least one irrational number. Turns out there's infinitely many, and there's more of them, so to speak. Here's a mind F for you. I keep saying mind F. I love it. You know, most humans use the word infinity a lot, but most of us don't really know what it means, right? We've encountered it in sort of a math class. But you can actually characterize different sizes of infinity. And that's actually not that difficult to see why once you think about it. For example, how many integers are there? Infinitely, right? Because every time you think you found the largest number, I just add 1 to it and my number's bigger. Right? You know, speaking, if you really want to nitpick the definition of an integer, you start with what is one of something. And then you say, oh, I'm going to construct the next thing, which is that plus itself, which gives me 2. And then you really construct them that way. Just the next integer is always created by the sum of the previous ones plus 1. Does that make any sense? Like 7 is 6 plus 1. But anyhow, not to go down that way. So if we're, I lost my train of thought. If you want to think about different sizes of infinity, if you trust me that there's more, you know, if we think of the interval from 0 to 1 as having infinitely many numbers, one of the questions you might ask is, can I order those numbers? Can I write them in a list? And it turns out you can't. And there's a very famous reason. Maybe we'll show you that later this semester, maybe not. But if I take another thing that's infinite, like the integers, I can list them. I mean, there's an infinite set. You can count them off. 1, -1, 2, -2, 3, negative, right? You're never going to finish that list because there's infinitely many of them. So we say that set is infinite. You're never going to stop. But there's larger infinities, so to speak, like the number line has infinitely many numbers on it, and we think of that as being bigger than, say, the infinite set of integers. So there's a lot of places this can go. So these are actually good questions that you're asking. Being curious is a very good thing. And again, this stuff is more or less difficult because when you don't realize, or excuse me, you know, you've kind of been working with numbers your whole life, but you've never really been forced to say why is it on the homework I make a point to say this is an integer or this is a real number, right? Because it matters when we're doing certain things. Okay, so let's get to this proof. We're now going to prove we will now prove the existence of at least one irrational number. So if we prove that square root of 2 is irrational, that's our first proof that we got, and we have at least one of them out there. As I mentioned last class, this is a famous example of what's called a proof by contradiction. So here's the logical idea. So the idea is to assume square root of 2 is rational. And show this contradicts some fact. So this is a logically sound way of doing things. Just like a logically sound way of proving P implies Q is to prove not Q implies not P. That's the contrapositive. Okay, so here we go. Let's sketch it out. as I said, one of the things we always want to do is we want to sort of realize that most proofs, unless we've seen them over and over again, are not going to be, one and done. You're not going to write it up without many trial and errors or revisions, as it were. A polished proof is usually not done in the first or second attempt. Okay, so here's what we're going to do. So assume P over Q is equal to the square root of 2 for some integers P and Q. So what I'm doing right now is I'm assuming this is the definition of being rational. I'm saying root 2 is a rational number. It is a rational number. Now, as I said earlier, there are lots of ways to represent the same number. And so in order to sort of make sense of this, we might know that 7 is equal to 14 over 2, 7 is equal to 7 over 1, 7 is equal to 21 over 3. There's lots of ways to represent, say, the number 7. Or the number 50 over 100 is the same as 1/2. 25 over 50 is the same as 1/2. So what we want to do, so that we avoid having to think about duplicate things that are the same, we can make one more assumption. So let's also assume P and Q have no common factors. So the fancy way of saying that is that their greatest common divisor is 1, the GCD. Now, what we're going to use now is we're going to use our previously obtained knowledge about numbers. So, if P over Q equals root 2, then you guys are well aware that P squared over Q squared has to be equal to 2. Or, another way of writing this is that P squared is equal to 2Q squared. So I squared both sides. So once again, here I am relying on a fact that we're assuming we all believe, that if I have an equal sign, I can do whatever I want to both sides as long as it's the same and I don't mess up the validity of the statement. Okay, now what does this mean? Why is this important? Well, this means by definition that P squared is even. Why? Because it's equal to 2 times something. Okay, this is great. We had a problem about this we did 2 classes ago. So we had a problem. We said if, now we went the other way, so this is where we have to be subtle. So if you go and think about the problems we did last week, or maybe it was even the week before now. We said if n is even, then n squared is even. Correct? And then we proved if n is odd, then n squared is odd. So the square of an odd number is odd. The square of an even number is even. Now, I am going to make a claim. And the claim is if P squared is even, then P is even. This is true. But let's think about why. If P squared is even, then P is even. Okay, that's hard to prove directly, but if I do the contrapositive, that would be if P is odd, then P squared is odd. And we already proved that to be true. So this means P is even. Again, if P squared is even, then P must be even. We proved this. We didn't prove it in that sentence. Actually, we might have. But either way, we proved it by proving if something's odd, then its square is odd. Now, you could verify this. Take any square number. Take 4. What's the square root? 2, even, right? Take any even square. What's the next even square? 16. What's its square root? 4. Right? What's the next even square? 36. What's its square root? 6. Right? I mean, you can convince yourself this is true, but we've also proved it. Okay, so if P is even, what? Well, if P is even, then P has to equal 2K for some integer K. That's the definition of being even. Okay, so now let's plug that in. Let's put that into the above expression. Well, that tells us that 4K squared has to equal 2Q squared. So all I did is I took that P squared that's 2 lines above and I replaced P with 2K, and that's how I got 4K squared. But here's the huge thing that we get out of this. This means Q squared is even. Because if I divide both sides by 2, I get 2K squared is equal to Q squared. But using the same reasoning we used before, we get Q is even. Okay, so where's the fallacy here? Where's the bad news? Yeah.
It invalidates our initial assumption.
Yeah, our initial assumption is completely invalidated now. But we didn't make any poor reasoning. Everything we reasoned was legal. The only thing that was a lie then, or the only thing that could possibly be a lie, is our original assumption. We started off with a lie, did everything else correct, and got to another lie. So let me state this again. So this means P and Q both are multiples of 2, which contradicts our assumption that they shared no common factors. And so the only logical conclusion is that P over Q equals the square root of 2 can't be rational. And that completes the proof. Yeah.
Back a slide real quick.
Oh, yeah, sure. Sorry.
Thank you.
Mhm. Now, what I would highly encourage you do, because it's no good for me to just do it right now. If you really want to understand why this is a logically sound way, is to think about this in terms of propositions, P's and Q's, not necessarily here. Okay, this is going to be confusing. What a terrible idea by me. I use P and Q for this, and you're going to be having heart failure because you're going to say P's and Q's before were in our truth tables and they were statements, and now I'm using them as numbers, and then I have to remind you context is key. Maybe I should have used A and B instead of P and Q. Oh well. You'll figure it out. So this comes down to a couple things. It comes down to the truth table for P implies Q. And what I would highly encourage you to do is think about, read it in the book. Read about, I think the author does a good job of describing why this is valid. There's no shortage of resources on the internet for you. You just Google proof by contradiction. I'm sure you've already Googled the square root of 2 is irrational. Hopefully you read different versions of that. They're probably going to be very similar to this. And then your job is to write up of your own version of this on your homework. That was problem, what, 10. Okay, does anybody have a question about this? Yeah. Oh, okay. So, we now know that there's at least one number out there that will be by definition called irrational. You know what's fascinating about this? We still don't know anything about the value of the square root of 2. There's lots of ways you can figure that out. The Babylonians had a pretty cool algorithm for it. Lots of cultures knew that it was roughly 1.4, but how do you do that? That's one of my favorite questions to ask students, especially like in calculus. You've all, you guys can get the square root of 2 from a calculator, but if I said, to give me a method for approximating the square root of 2, could you do it? Give me a method for approximating pi. Okay, let's do these other problems now. So I'll let you guys work on number 11. I believe, Michelle, you asked about 12 and 13. Let me double check. Yep. And so we're going to do that. So one of the more, let's sort of transition into this. So an important sort of theme, not just in advanced math, but in other places. But since this is a math class, inequalities arise in advanced mathematics, and not just mathematics. I mean, any branch of science that uses mathematics, these things arise. So let me just give you a couple important sort of examples. Many of you have probably taken a chemistry class or maybe a physics class, and maybe you've heard about things like quantum physics, or one of the things that humans have been studying for a while is trying to understand things like the hydrogen atom. You have one electron floating around this nucleus, and it turns out that it's not as easy as you might think to understand its properties. And we invented a whole sort of a whole branch of physics to try to do that, called quantum mechanics. And one of the things we find is that there's a thing called the uncertainty principle, which is mathematically an inequality. So this particular creature right here, is an inequality. Not that you care so much about it, but it is. Some of you will get to learn about all this fun stuff at some point in your life. And it's named after this dude, Werner Heisenberg, who was I'm pretty sure was a German physicist. And it's called the Heisenberg uncertainty principle. So I always find it interesting. There was a real popular television show on like 10 years ago called Breaking Bad. You guys familiar with it? Maybe you watch it. Yeah. So he called, his nickname for himself was Heisenberg, based, given, in credit to this dude. But anyhow, there are tons and tons of inequalities that are extremely useful. And if there's no shortage of resources to sort of learn about all these things in every branch of science and mathematics. And why do inequalities arise? Well, sometimes we can't get all the information we want. We can't figure out everything, so we then say, what's the best we can do? What can we learn? And again, I would encourage you to just maybe, when you're bored one day, you can go read about this. Like in probability, you guys have learned about Chebyshev's inequality, Markov, and these ideas of being within so far of the mean. You get to learn about some of this stuff. All right. So anyhow, we do this in computer science when we're talking about run times of algorithms. How do we know how long it's going to take, or at least what is the maximum time something should take, or what is the minimum amount of time something should take? So anyhow, that's sort of my advertisement for why you should give a damn about inequalities, even if you don't. But nonetheless, an important skill, even if you don't care about all that, is being able to develop or derive inequalities. And so one of the homework problems that we asked you to do is one like this. How do we prove that no matter what value of x you have, it satisfies this expression as long as x isn't 0? Now, you might say, well, it's true because I go to the graph and I see it's true. But that's not what we're asking you to do. We're asking you to use the laws and the basic definitions of numbers, how we do things to verify this. Now, you can choose a couple values for x to convince yourself that it's true. But how can you prove it? Turns out there's lots of different ways of proving inequalities. Some strategies work all the time, not all the time. Some strategies are better in certain situations than others. But how could we perhaps prove this? So let's look at something. So when proving inequalities for real numbers, it's useful to have a starting point, to start with a basic fact and quote unquote work with it. So one of the nice things that that is a basic fact that we can always use, and by the way, you've sort of seen this for those of you who've had calculus, at least with me. One of the things we ask you to do is we ask you to remember that there's a basic inequality with a trig function, sine and cosine. And we often work with those inequalities to prove things about when we were doing things like with the squeeze theorem and limits. So that was an example of these kinds of ideas. But we're not trying to prove that right now necessarily. So let's try something else. So let's look at an example. Let's just play a game. Let's start with something we know to be true. So let's say I know that I have a minus b quantity squared. I don't care what a and b are. I don't care. But I know this is a fact no matter what. You take any two numbers and take their difference. I don't care if it's positive or negative. If I square it, it becomes what? A positive number. So this inequality is a basic fact. Right? There's nothing, that is a fact. Okay, so let's see what it gives us. So if we multiply it out, I'm left with a squared minus 2ab plus b squared is greater than or equal to 0. Okay, is that useful? Maybe it is, maybe it isn't, but let's rewrite it. If I take that AB to take it to the other side, if I take that to the other side, I can write this as a squared plus b squared is greater than or equal to 2ab. Now, this might have some useful things. Maybe you draw a picture of a rectangle. That might seem to make sense. I don't know. But we can play the game even more. Perhaps I want to get something else out of this. Is this give me anything? Is it useful at all? So one nice thing to note is maybe you take this thing and you say, oh, okay, this is pretty cool. What if I rewrite this, though? What if I take one thing we know about, for example, maybe this tells us that a squared plus b squared over 2. So the average of the square of two numbers is always at minimum a times b. So let's just leave it like this. Maybe this is cool. Maybe not. So the first thing I need you to understand is, look how this problem started off. I'm not saying prove anything. I said take a known fact and play around with it. It's kind of like a kid goes into a sandbox. Maybe they want to play with this shovel for 5 minutes. Maybe they want to play with this toy the next 5 minutes. All I'm asking you to do is play. Maybe this thing is useful, maybe it's not. Let's try something else. Let's try this instead. So I'm going to start with a minus b squared greater than or equal to 0, like we said before. Only this time, when I multiply this out, I have a squared minus 2ab plus b squared greater than or equal to 0. But maybe I'm interested in trying to figure something else out. Or maybe I recognize, okay, what if I started with, by the way, that thing on the left, we call it a perfect square, right? It's something squared. But what if I wanted to sort of massage this thing a little bit and get another perfect square out of it? So I can make this little subtle trick. And it's not exactly sure why I would do it other than maybe I have experience that tells me this might give me something cool. Yeah, right. So here's one. Well, you got to be careful. You don't want to do plus. You have to rewrite it. So instead of writing minus 2ab, we're going to do minus. So a better way of writing this is put this as plus 2ab plus b squared. And I can't just do that, because if I do that, I've broken the law. I've cheated. But if I put minus 4ab here, now this is legal. I've just rewritten it a different way. Now you're going to say, why the heck would I do that? Well, because now I have another perfect square. I have a plus b now, quantity squared, is greater than or equal to 4ab. So because I have experience and I've seen these ideas work before, I know that I can get a perfect square if I just rewrite a couple terms. So instead of writing minus 2ab, I said I'm going to write plus 2ab minus 4ab. And then that allows me these first three terms in the second line up is also a perfect square. Now, who cares about this? You know, in the line above, I said maybe this is cool, maybe this ain't. But this actually turns out to be very, very useful, what we just found. It has a famous name. And so I just need to rewrite it. So we can rearrange. Right, so I'm going to take the square root of both sides, and I get a plus b is greater than or equal to 2 times the square root of ab. Right, so this is what I got. Take the square root of both sides. Now I divide both sides by 2. And now I have a plus b over 2 is greater than or equal to the square root of ab. Now this actually has a name. This is a famous inequality. Typically it's called the AMGM, or arithmetic geometric means. So what I mean by that is there are different types of averages. So the one you're most familiar with is the arithmetic mean. And then there's the geometric mean. And this is a very simple example of a much more difficult and famous type of problem, which are called the isoparametric problems, which is given some curved region, what is sort of, if you have some, say you have fencing, and you can put in fencing in any different way, how do you maximize space enclosed type stuff? Now, of course, these are famous, like some of them are simple, like if you have a curved region, the maximized area inside a fixed circumference, it's going to be a circle. But oftentimes in the real world, we have things like restrictions and constraints where these things become much more difficult. Okay, so there's lots of ways to have derived this inequality. Now, the question you might have, for example, Michelle, what if I said to you, if I just said to you, prove this? Well, look, that discovering I have done can be reversed. If you start with this, you can start with something and revert it back to a basic fact. So if I just reversed my process, that's the same thing. So if you want a hint, for example, on number 12, start with what I gave you and see if you can work it down. See if you can do things like take square roots or do algebra and work it down to something that is a trivial fact. I'll give you another hint. Can you recognize, where's it at? I lost it. Okay. Is there somehow, some way you can get a perfect square involved? Is there a perfect square hidden there? So I'll give you a hint for number 11. And I'm not saying you have to go this way. Not number. Yeah, number. Hint for number 12. Note that x plus 1 over x quantity squared is equal to x squared plus 2 plus 1 over x squared. That's my hint. And so what does that mean? That I just gave the damn problem away. Shoot me. That means that this is this. So see if you can, one of those is useful, the other's not. See which one you want to use. I just did the damn problem for you. So, oh well. Put the puzzle together. And by the way, before we go, how many solutions did we find for 13? Anybody say there's just one? Anybody find any solutions? Yes. No? You didn't find any?
I didn't
Oh, you didn't look at it yet? Oh, well, I'm gonna look at it. So I'll give you a hint. There's infinitely many. Now, wow, this thing's breaking. And the question then for you becomes, why? Then another fun problem, can you write a code that finds them all? Or at least the first 100 or the first 5,000. It's not hard to do. Computer can do it real quick. Pick a number. Look, don't make this harder than it has to be. Pick a number. You can guess an easy one. I'll give you a hint. Back in middle school or in high school, you learned about something called special right triangles. Think about what this thing has to do with right triangles. And think about special right triangles, and you'll find, yeah.
Isn't it kind of like the definition of a vector?
No. No, I mean, you could somehow, no, you might be thinking about the length of a vector formula,
Okay.
but that's not this. This is an equation. Basically, I'm saying find three numbers, x, y, and z, that when you plug them in, it's true. I mean, clearly 0, 1, and 1 works, but that's kind of boring. 0, negative 1, and 1 works. There's lots of, I mean, if x is 0 and y and z are 1, it's true. Anyhow, think about it. I'll show you some cool stuff on Wednesday about that. All right? Any other questions? We got to go. We're out of time. Thank you, guys. Have a good one. Stay away from trouble. And I will talk to you on Wednesday. Bye now. Thank you.